All right. So we learned that in order to predict what kind of, to find out what is velocity and what is acceleration, we will have to calculate derivatives of position and velocity appropriately. And when we calculate derivative of a vector, knowing its scalar component, we get a vector whose components are equal to derivative of the components of the original vector, correct? All right, what I would like you to do is learn derivative of the most common functions. Memorize the derivative of the most common functions, so power functions, trigonometric functions, the functions which you have at the back in the the ones which we are going to use. So definitely we will have power function and trigonometric functions, and I think exponential and logarithmic, and that this will be all functions for which I want you to remember derivatives. Also remember the formulas, how to calculate derivative of product of functions, quotient of functions, sum of functions, and a composite function. Also, it would be good actually that you know how to calculate derivative if we multiply a function by a certain constant. All right. Today I would like to still to work on an example. This time I would like to analyze a motion for which the equation for position will not be as simple as the one which we did yesterday. Yeah, because yesterday, if we were smart, we could choose a coordinate system in such a way that two scalar components of positions were 0 and only one was varying. One was a linear function. Actually, the function which you have, which I put on the quiz today, each scalar component is not a 0, which was, however, that motion is also motion with constant velocity. It is simply that it was described in a coordinate system which so the motion was not along an axis. Well, sometimes even for a motion with constant velocity we won't be able to do it, because imagine that we have two objects. Yes, let's say that one is moving in this direction and another is moving in this direction. Then there is no way that we will find a Cartesian coordinate system that each motion is along an axis. If I choose this motion along an axis, then this one, in the best case, will be along a diagonal of these two. If the two motions were perpendicular to each other, I still could do it. So one object would move along one axis, another object would move along another axis. Well, however, this motion which I wanted to show you today doesn't even have such a property. I'll try to figure out now what happens in this motion. Okay. Really, I will not give you at least today, reasons why the motion is described by quadratic function. When we will learn a little bit about interactions, we will see that it's a very reasonable approximation. However, it is approximation. It is the equation which I'm going to write will assume that that Earth is flat and there is no air on Earth. And if this is the case, the so trajectory is in the shape of a parabola. If I choose a coordinate system in a smart way, I can write it down, I can write the equations for that motion still in a relatively simple case. In general, actually, I could write down that position is equal to position at a certain instant to which we assign, at instant 0 plus velocity at instant 0 multiplied by time plus 1/2. Actually, I don't want you to think about it that it's velocity. I don't forget what I said. This is second vector, and here I have another vector. Position at an arbitrary instant t is a quadratic function of time for this motion. Now, if I choose coordinate system like this, actually, so let's say that this axis is x, this axis is y, and z will be toward us. I'll mark z toward us that way. I have to adjust now these vectors r0, v0, and a to such values that they match this particular trajectory. So, for example, if I selected coordinate system in such a way that the motion starts at the origin, and let's say that this is when the object is released, we assign instant 0 to that event. It would mean that if I plug in 0, I should the formula over there should give me the location of the particle at that instant. So, what should I choose for R0? If I plug in 0 here, the particle should be here. What are the coordinates here? 0, 0, 0, correct. Okay, so how to adjust this vector, and this vector so that this formula leads to that. Consult with each other. How should I adjust the values of those three vectors so that when I plug in value 0, because this equation is supposed to say where a particle is at an arbitrary instant. Whatever we think for that instant, if we plug in t for that instant, we should get position of the particle. So, for example, if I plug in 0, I should get this position. Well, let's see what will happen if I plug in 0 over here. What will happen to this term? Why 0? Why this term will become 0? Well, every object has starting position 0? No. Oh. Actually, on the quiz, I saw something that, because probably what you mean is that the distance traveled by the object is 0 meters. Make sure not to confuse distance with position. Just formally, let's simplify this expression. What am I going to get if I plug in 0 here? So, plug in 0 to this term. For t. What will happen with this term? Nothing. It will stay like it is. It's R0. What will happen with this term? What 0? T is 0. How about the entire term? Is it this 0? No, it's not this 0. What 0? Vector 0. Correct. This becomes 0 vector. Which means what are its scalar components? 0, 0, 0. Correct. Now we plug in 0 for t. What will happen to this term? Will be also 0 vector. By the way, what plus do we have here? Vector addition. Correct. What multiplication do we have here? Vector times scalar. Yes, so this would be a bullet. I'm abandoning already unambiguous notation. I hope that you learned it. However, think all the time what you use. All right. So we figured out that we've plugged in 0 over here. The only term which will remain is R0. Right? And we want the particle to be at 0, 0, 0, which means that R0 is equal to this vector, 0, 0, 0. Scalar components of vector R0 in this drawing are 0, 0, 0. Do they have to be 0, 0, 0 always, in any circumstances? Forget now about this situation. No. If this is a building, for example, and you release an object from there, then this position at instant 0, which for some reason we call it initial position. It doesn't make much sense to me, because 0 is like any other instant. 0 is like any other number assigned to an instant. So it would be better to say position at instant 0, rather position at the reference instant rather than initial. However, entire world uses phrase initial. You have to recognize that it is initial, because there will be engineers who will call it that way. So we recognize that R0 has a meaning of initial position, which refers to position at instant 0. But in general, it could be anything. All right. Now, let's find out then velocity at an arbitrary instant t. Scalar components of velocity. Help me with that. No, at any instant. I want now to find velocity at any instant. Well, we could actually do it in many ways. One way, because how do we find scalar components of a derivative of a vector? Derivative of individual components, right? So in principle, we could take derivatives of individual components. I will complicate it kind of at this moment, because I can have a shortcut and find it out faster, but just to see how that thing works, why don't we explicitly write down components, all three components of position. So what am I going to have here? What is x component of this vector? Well, I have to add x component of this vector plus x component of this vector times x component of this vector. X component of this vector, over here we had 0, 0, 0, but in general I can say that it is set in x. I will call it x0. Now, x component of this one, I will have to take x component of velocity and multiply by t, this velocity. So consistently I will have to put v0x times t. Now for this expression, I will have to have 1/2 x component of acceleration times t squared. How about if we go then for x component of velocity? right? Because we have already written x component of position. What do I have to do now in order to get x component of velocity? Can you help me? Take the derivative of this function. Right, help me. Derivative of this constant. 0. I won't bother writing. Here we have a linear function. Derivative, so it's a certain constant multiplied by variable. Derivative with respect to this variable will be just this constant. It's a linear function. It's a power function, so it's t to the first power. Derivative will be 1 times t to 1 minus 1. So will be v0x plus, now derivative of this function. Here it is a quadratic function. We have a certain constant multiplied by quadratic function. So I take a constant, 1/2 ax, and derivative of x squared is t squared is 2t. So I will get a x times t. Right, now the second, let's come back to the explicit form of the second component of position. So I have to take second component of the first vector plus second component of the second vector plus second component of the third vector. Why don't we find the derivative of this function? Quickly. v0y plus ayt. All right. Well, we can recognize that for the last component we will have a very similar expression. Where? Well, 2t cancels with 1/2. Over here I have 1/2 ay as a constant, and then the derivative of t squared was 2t. So 1/2 and that 2 cancels, so I don't have 2t here. All right, this was kind of a hard way. I could really, oh, well, how about if I write it down different way? AZ, correct. It is Z. I mean, I just didn't write it neatly. I can write down now this as a sum of vectors. Okay, I see that this is a sum of a vector whose components are v0x, v0y, v0z. Do you see that? What is that vector? This is that velocity v0, correct. I mean, it's this vector, v0. I don't even want to call it velocity. I'm sorry that I said that it's velocity. We'll find out that really it is. And what is the second vector? Well, the second vector has components axt, ayt, azt. And that one happens to be a product of a vector and time, right? What is that other vector? At, correct. Now, I didn't really have to do it this way. I could really perform operation over here almost like on numbers. I can recognize now that here I have a vector whose component, and well, because when I calculate derivative, I will have derivative of a sum of functions over here. So it is going to be derivative of the first term plus derivative of the second term plus derivative of the third term, despite they are vector functions. Now, derivative of this vector will require that we calculate indeed derivative of the first component, second component, and the third component. But all components of this vector are 0. Therefore, derivative of this vector is going to be what vector? 0 vector, correct? So the first will be 0 vector. Now here I have this vector times t. Now look that each component is a constant multiplied by time. So the derivative will give just the constant. So practically, calculating the derivative of this function is like, well, that it's a constant times time, despite the constant happens to be a vector. So I can write down the derivative of this function is just a constant. And over here, the constant is going to be 1/2 times this vector. I multiply by 2 derivative of t squared, which will be 2t. So 2 and 2 cancels. I will have vector A multiplied by t. So you don't have always to write down the function explicitly in terms of scalar components in order to simplify the expression. Now, in order to see what is the meaning of symbol V0, look what will happen if I plug in t equals 0. What is value of velocity at instant 0, according to this formula? Which one? Just this thing, right? So it will be just V0, which means that this number this vector over here represents velocity at instant 0. And because it represents a quantity at instant 0, we assign again the same adjective, that it's initial velocity. So V0 is the initial velocity, but really what it means is that it's velocity at instant 0. Why don't we find out acceleration now? And how about if we now make a shortcut? We don't explicitly write down the components, but calculate from this expression. So help me to differentiate now this expression. What will be the derivative of this function? Because it's a constant, correct. So the derivative of this function is a 0. What 0? 0 vector, correct. So what are the scalar components of this the derivative? 0, 0, 0. All 3 components are 0. I won't bother to write it down. Let's find out scalar components. What will happen if I calculate the derivative of the second term? In other words, what will happen if I differentiate the second term? I will just get an A, correct. All right. And actually, how about, can you give me that bullet from there? And in the meantime, I will use another one. And I will give you a puzzle. Now, these equations over here describe how that ball moves. Did you get it? Thank you. Why don't you now defend that part of the room against the second bullet? I will give you a puzzle. I want you to figure out what is the acceleration at the highest point. Oh, let me load it stronger. So you saw that the ball is first flying upward and then turns downward. Okay, thanks. And I want you to have a brief debate with each other to come out with the answer. What happens with the acceleration as the ball passes through the highest point? And rather than giving me stories, give me a firm argument found on the whiteboard. Talk to each other. Okay. What's your answer?
The acceleration is 0.
At the highest point, acceleration is 0. Who agrees with this? Or who disagrees with this? Aha. There is some opposition, very weak, but there is. Well, let's now have arguments for defending the two values. Where do you see on the whiteboard that acceleration is 0? Yes? It's what? Yeah, we're talking about that instant. Yeah, when the bolt passes through this instant. Where do you see it?
The derivative of the velocity will be a constant at that point in time.
Well, no, hold on. Whenever you calculate derivative of anything and plug in particular value for that derivative, everything is constant over there. Yeah, constant means that it doesn't change. So you cannot say that something is constant at a single instant. Constant means that it is at this instant and the next instant it is supposed to have the same value. Cannot be constant just at a single value. So yes?
Is it because the slope of the tangent line is 0 at the vertex of that curve?
Okay.
If you find the derivative, doesn't that give you the slope of the tangent line?
Yes, it does.
Okay, so at that vertex of the curve, the slope of the tangent line is 0.
Well, but then I would have to actually to calculate the derivative of a completely different function. I would need a function y of x, and derivative of this dy over dx is indeed 0 over here. But
And if you took the second derivative, which would be acceleration, wouldn't it be 0?
well, it's already that one is already.
That's the second derivative.
No, this is first derivative. It's 0. Uh-huh. Okay. Well, how about you? You disagreed.
Well, I was kind of confused because isn't gravity constantly accelerating the ball?
I haven't heard about gravity yet. I have no clue what are you talking about. Use only things which are on the whiteboard. How from the equations on the whiteboard you see or you don't see that the vertical component of acceleration is 0 or not 0? Well, how about if we, before that, why don't we actually write down what, in this coordinate system, what are the scalar components? Let's say that the ball travels in this direction with, that the magnitude of this velocity is 1 meter per second. So, and how about if we think that this is, well, 45 degrees. It will be easier to find out. 45 degrees. So, what are the scalar components of vector v0? Actually, how about if I write down r0 is going to be 0, 0, 0. Now, v0 is going to be meters. It travels 1 meter per second that way, so x component will be 1 over square root of 2, or square root of 2 over 2. Square root of 2 over 2, square root of 2 over 2, 0 meters per second. Now, well, to find out that acceleration really, in order to in this coordinate system, scalar x component and z component of the acceleration are 0, and the vertical component is negative, and it's 0, 0 minus 9.8 meters per second. All right. Well, so which means that I would have to use these vectors to predict position, velocity, and acceleration. Now give me the argument. Yes?
I have a Why at v0 you already have a velocity? Wouldn't that be v1?
This is not velocity, this is magnitude of velocity.
Right. But the vector components at v0 you have values for also. It wasn't moving at time 0.
Well, nothing is moving at a single instant. Motion is associated with time passing by. So you can never say that because that way, I mean, if you plug in any value for t, it is going to be at particular location. Particle is going to be at particular location, but from that you cannot say that the particle is not moving because it is at particular location. I mean, you will have a very good argument actually in the court when you get a speeding ticket that way. Because you say that at an instant you were at that location and that's it. You have to imagine what happens an instant later. And this is what you are getting ticket for. That you are doing, that your position is measured at 2 instances. And displacement is compared with the time in which you made this displacement. And this is what velocity is. Although they are giving you tickets for a quantity which we don't know yet, speed. We are not, I know that a lot of you confuse speed with velocity now. We'll talk about speed next week. All right. So, because so far you gave me only stories why acceleration is 0 or why it is not 0. Yes?
I'm confused how your velocity equals that if you're at position 0, 0, 0. If you're at position 0, 0, 0, how's your velocity equal? I thought your velocity would be 0 as well.
No, you don't see time again. It comes from this equation. You have to plug in value 0 over here. When you plug in over here 0, oh, I know what you mean. Well, let's try to figure out where the particle where the particle is when if this is 0. How the particle would move. It means the particle would move let's say at instant t would be 0, 0, 0 plus 0, 0, 0 plus 1/2 0, 0 minus 9. Let's put minus 10 meters per second square times t squared. Let's see where the particle is going to be. Well, at instant 0, it is going to be 0, 0, 0 at the origin. Is it right or not? Correct. Let's see where the particle is a little bit later.
Where are you getting negative 10? Is that gravity
It's not gravity. It's indeed a constant which I would have to put in to recover this trajectory. In order to get this trajectory, this is how I would have to put what value I would have to put for acceleration. Yes?
Position 0 is the particle at rest.
Moving. I mean, it's the beginning of that motion. So instant 0 is soon after the ball leaves this barrel. Good. Right, so as that ball leaves the barrel, this is instant 0. And it is traveling. Now, if you use a high-speed camera and took a picture, on that picture the ball would be here. But from that picture you wouldn't figure out what is velocity of the particle. How would you have to, using camera, find out velocity of the particle? You have to take 2 pictures. At the instant where it leaves and a little bit later, and see by how much the particle was displaced. You will have to know in what is the time between the 2 pictures, and then you would be able to find out velocity. You cannot find velocity from a single snapshot. It's something like trying, in general, if I have a certain function, and I will tell you that the value of the function at this, for this argument is this much. Find the derivative of the function. Or what is the slope of the plot? If I gave you just 1 point. Do you see that? Yeah, I know that you are still not sufficiently familiar with the derivatives, but derivatives requires that you first imagine what? Yeah, because when we calculate derivative, we take limit of that quotient. What do we call that quotient? Difference quotient. So you have to be able to see a difference quotient. Well, so if I know that, for example, it's at this instant or at this argument, value of the function is like that, I already can at least imagine a difference quotient, and well, figure out that derivative will be close to that slope. And now I can think that I have the function. Now you have too much information, yeah, because this different quotient doesn't matter. All right. So let's come back to here. And I still didn't hear really a good argument for the vertical component of acceleration. Yes?
At the top of the curve, your vertical velocity is going to be zero.
Vertical component of velocity is 0. I don't know why, but so what? What does it say about acceleration? No. Again, the same problem. From one value of velocity, you cannot determine anything about the derivative. You will have to know what happens with velocity at the highest point and a little bit later in order to determine derivative. Your opinion is?
You know that the acceleration is not 0 because the derivative of velocity would be the rate of change of the velocity, and the derivative is the acceleration. And since the velocity is changing, then...
well, I got it. It's actually, I am convinced, although I know that most of you are not. You don't know what he said. I understand. Who understood what he said? So what did he say?
He said that since the change is between the two infinitesimally small points, the velocity is 0, the derivative of that change would be 0.
Is this what you said? No! Because, what's your name?
Colby?
Colby said that velocity doesn't change. Yeah, at the highest point and a little bit later, velocity doesn't change. It has the same velocity at the highest point and later. Therefore, acceleration is 0. Now, he said that velocity is changing. It has one velocity at the highest point, a different velocity an instant later. Therefore, acceleration is not 0. Colby said that it is 0. Do you recall that? Is this what you meant? Did I reflect? Did I repeat your thought properly? Yes. Did I repeat your thought properly? Mm-hmm. Yes, correct. I'm confused. Who is right then? Yes.
What you're saying is because velocity is constantly changing, and acceleration relies on velocity, then your acceleration will constantly be changing.
No, we don't. No, this is not what he said. He said that since velocity is changing, then acceleration is not 0. We don't know if it is going to be constant or not.
Not constant, but you're continually changing.
The velocity is continually changing, therefore acceleration cannot be 0. This is what he said. All right, so who believes now that acceleration at the highest point is 0? Or who believes that the acceleration at the highest point is not 0? Have conversation now with your neighbor, because, well, I see that a lot of you changed your mind. Yes? Consult with your neighbor now. Consult with your neighbor. I think that, I mean, you are already, because
But it's then coming towards this direction. Why is that vector coming towards us?
The acceleration is positive. That's
well, okay, so I think that now you have a good idea. Well, I am just curious. So who believes that acceleration at the highest point is 0? Who believes that it is not 0? I was actually hoping that after the, I mean, I see that that the number increased. It's not as far as I thought. However, I'm still happy. A lot of you got convinced that acceleration at the highest point is not 0, and actually you saw it here. What does this thing say? That acceleration at instant t has this particular value. No matter if it is 0, 0, minus 10 or 1, 2, 3, it is not a function. It's the same set of numbers that we had here. If position is a quadratic function of time, then velocity happens to be a linear function of time, and acceleration is constant. It does not change in time. This type of motion is referred to as the motion with constant acceleration. Whenever you have position dependent on time through a quadratic equation, acceleration is constant. Now, I know that you could debate that the ball really was moving along the quadratic equation, and here I would give you credit. This is true. As I said at the very beginning of this class, the ball moves along quadratic function when we assume then Earth is flat and there is no air around us. If we take into account that Earth is round and consider interaction with air, the conclusion will be completely different. By the way, quadratic equation was not the first one which described the motion of a flying ball. Really, it was a very popular subject in the Middle Ages when we invented cannons, because And because of that, actually, this motion is also referred as projectile motion. The quadratic equation describes motion of a cannonball. And if we had a castle, and now this is not a particularly popular subject, we don't shoot castles or other departments over here with cannons, but there was an earlier theory which was saying that cannon actually moves along. I made a little bit too big castle. How about castle this big? That the projectile travels along a straight line upward as long as it has something which was referred as impetus, and when all the impetus was gone, the ball turned that way. This was earlier model. I mean, our model over here says that it is going to travel along a parabolic trajectory, which is also wrong. Really, it is going to move along so-called a ballistic curve, which looks like that. It's between those two. All right, so this will be all for today, and see you tomorrow.
Our test covers 1, 3, and 4.
No, not 4.
Not 4.